All right, so here we go again, continuing with Newton's laws. So just a refresher, Newton's laws were developed after Sir Isaac Newton. He created these three laws to explain kind of why things move the way they do. He was credited with kind of the units for force due to these three laws relating to force. The unit for force is a Newton, which is equal to a kilogram meters per second squared. So that brings us into then Newton's second law. So Newton's first law is an object at rest remains at rest, and an object in motion remains in motion unless acted on by an outside force. Newton's second law states that when an unbalanced force acts on an object, the object will accelerate in the direction of the force. Okay, so let me just talk that through in simple terms. It requires objects, in order for objects to accelerate, they require a force. Okay, the amount that objects accelerates is proportional to the force applied and the mass of the object. Okay, if you push an object harder, it will move faster. However, if that object is heavier, if you push it with an equivalent force, it won't move as fast. Okay, this formula is important. So Newton's second law can be stated essentially in a formula where F equals ma. F equals ma. And because those two variables are side by side, they are multiplying. So force is equal to mass times acceleration. All right. Mass, like we said before, has to be in kilograms. Acceleration has to be in meters per second squared. And that then leaves us with force in newtons. And we'll do some calculations with this in a bit. Now, conceptually, we need to understand what Newton's second law is. All right. I kind of just explained it, but the idea is the larger the force on an object, the larger the acceleration. Okay. So if you have two objects that are the same mass, if you increase the force to the object, you will increase the acceleration, right? Throw something harder, it travels faster. Makes sense. Now, mass is going to work kind of against acceleration, right? Heavier objects are harder to accelerate. So if you increase the mass of an object, that will negatively affect the acceleration, right? If you're trying to move something heavier with the same amount of force, it won't accelerate as fast. Okay, that's the idea there. Think about trying to throw a basketball and trying to throw a medicine ball, which are those weighted balls, with the same force. Okay, the lighter ball is going to accelerate faster than the medicine ball. Okay, those are concepts that relate to Newton's second law. Now, let's talk about how this works in calculation. Okay, a skateboard has a mass of 9.3 kilograms. How much force is required to accelerate the skateboard to 1.5 meters per second squared if the skateboard is traveling downstream? Okay, so my mass here, let's always start by writing down the information we know. Mass is in kilograms, good. We're asked to solve for force, and my acceleration is 1.5 meters per second squared. Okay, with these three variables, I'm using my force formula, F equals m times a. I'm solving for force. I plug in my mass times my acceleration. Okay, so no big tricks here. Mass times acceleration, you simply multiply, and that equals 13.95. And again, my units here are kilograms and meters per second squared, but that is equivalent to a Newton, all right? If you put kilogram meter per second squared, that would be correct as well. But typically, forces are written in newtons. Okay, that's all there is to that. Example 2. A force of 400 newtons is applied to a skateboard at the top of a ramp. A skateboard has a mass of 8 kilograms. What will be the acceleration? Okay, force of 400 newtons, mass of 8 kilograms, and now we're solving for acceleration. I still have the same three variables, so I have the same formula. I plug in the information I know. Okay, and I'm solving for acceleration, so I leave that as a variable. Now I have to do basic algebra. I have to solve for acceleration, so I have to move that mass. Okay, whenever you're trying to move something, you do the opposite operation, which in this case is division, is the opposite of multiplication. And whatever you do to one side, you have to do to the other side, the equal sign. Those cancel out, which leaves me with A equals 400 newtons divided by 8 kilograms, which works out to 50, and my units for acceleration are meters per second squared. And that's that. Okay, last example here. A freight train slows down as it approaches a train yard. If a force of negative 3.8 times 10 to the 5 newtons is required to provide an acceleration of negative 0.3 meters per second squared, what is the train's mass? Now remember that with vectors, direction can be indicated by negatives. So in this case, in order to slow the train down, we have to apply an opposing force, which is why my force is negative. And because the train again is slowing down, my acceleration is negative here. Okay. All right. Now we see this number is in scientific notation. You could input that number into your calculator if you're comfortable, or use your knowledge from earlier in the unit to convert this back to a kind of standard notation number. Now again, the negative is just applying to the direction, so that would stay. And then 10 to the power of 5. My power is positive, which means I'm moving the decimal right 5 times. So 1, 2, 3, 4, 5. Fill the spaces with zeros. So that becomes 1, 2, 3, 4, 5. That is 380,000 newtons. Those two numbers are equivalent. Okay, but I'm going to write this down. I'll put it in standard notation, but again, you could just plug that into your calculator. Just make sure you know how to use exponents. Acceleration is negative 0.33 meters per second squared, and I'm solving for mass. Okay, F equals M times A. Put my force in, and I do include my negative, even though it's just indicating direction. Oops, running out of room. Okay, algebra, opposite operation. I divide by negative 0.33 meters per second squared, and I do the same thing to both sides. Now you'll notice here when you're dividing by the negative, when you're dividing a negative by a negative, they will turn now into positive. So mass equals, just double check my math here. Okay, it's a fairly big number here because we're talking about trains here. All right, there you go. So when you're dealing with this formula, basically, if you're solving for acceleration, you're dividing out mass. If you're solving for mass, you're dividing acceleration. Okay, and if you're solving for force, you just follow the formula. All right. Last of Newton's laws is the third law. This can be called the law of pairs or the action-reaction law. Basically, the idea is for every action, there's an equal and opposite reaction. Okay, so this means that all forces occur in pairs. So even though you may not think about it, if you were to push on the wall is actually pushing on you with an equal and opposite force. Okay, so we can actually use a lot of things that kind of, and a lot of motion that occurs in real life operates on Newton's third law without us even really thinking about it. So if we think about rockets, for example, we know that rockets propel upwards, but in order to do that, they actually have to exert a force downwards. So there's a chemical reaction, obviously, that will create a lot of pressure. That exhaust is actually going to propel downwards, and that will create an equal and opposite force pushing the rocket upwards. Okay, you can create a rocket bottle with just a vinegar and baking soda reaction if you wanted, and see that kind of happen. If you put a cork in a soda bottle, the cork will kind of push downwards, showing you that there's a downwards force and the rocket will propel upwards. Okay, so this is shown here. We're not actually going to do formulas or equations with this, but what it's telling us is that the force of object 1 on object 2 is equal to the force of object 2 on object 1, but they're opposite. Okay, so I want you to just think about motion, for example. Think about skating. If you're trying to skate forwards, which way do you have to actually push in order to do that? So in order to move forwards, you have to kind of push your skates and push against the ground backwards. You push on the ice backwards, the ice pushes you forwards. Okay, think about jumping. If you want to jump upwards, you actually have to think pushing downwards, right? Think about it kind of, let's say, trying to jump really high in volleyball, right? You squat your legs and you push against the ground downwards, and the ground pushes you upwards, with an equal and opposite force. Kind of weird to think that way, but it's the case of a lot of things. Think about swimming. Again, if you're trying to swim forwards, you have to push the water backwards. Okay, canoeing. Which way do you push the paddles? You push the paddles backwards and the canoe moves forwards. All right. Hopefully you can think through that a lot. You can read that one by yourself. I want to just identify again. So forces act in pairs. When two objects collide, they are actually experiencing the same but opposite force, opposite direction. So, let me just talk about this example here. It's a common misconception that when two vehicles collide, if one is smaller and one is larger, people think that the smaller vehicle experienced a larger force from the large vehicle. But this is not true, okay? According to Newton's third law, both vehicles experience the exact same force. But the reason the smaller car would experience more damage is because that same amount of force on a smaller object causes more of an effect than on a bigger object. Okay, so again, thinking about Newton's second law a little bit there. So they're actually experiencing the same force, but the kind of more massive object, that force will kind of dissipate a little easier, right, than the smaller object. All right, so let's just, again, thinking about those force pairs, that action-reaction. If a weightlifter is pushing the bar upwards, and that's the action force, the reaction force is that, in fact, the bar pushes down on the lifter, which is what supplies the resistance. Okay, in bowling, the ball pushes the pin leftwards, or left. The reaction force, equal and opposite, the pin pushes the ball right. All right, so all of this, Newton's third law is about equal and opposite forces. All right, if we have a balloon, air is pushing the balloon outwards, but the balloon is also pushing the air inwards. That's what creates that tension. All right, at this point, hopefully you've got a bit of a rundown of Newton's three laws. All right, Newton's first law, an object at rest remains at rest, and an object in motion remains in motion unless acted on by an unbalanced force. Newton's second law, basically the idea is that force is equal to mass times acceleration. If you push an object with more force, it will accelerate faster. If that object has more mass, however, it will accelerate slower. Okay? And the third law is the law of action and reaction. So every action force has an equal and opposite reaction. Okay, at this point you should be working on your workbook, and there's a few other additional videos that I will post that will help you with Newton's laws. There will also be a small quiz on Newton's laws and that force calculation as well. All right, good luck.